Welcome to 11th lecture of module 5. In this module, we are discussing distillation operation. Before going to this lecture, let us have brief recap on our previous lecture. Last lecture, we mainly discussed one important thing, which is multi-stage batch distillation with reflux. Multi-stage batch distillation with reflux can be run in two different conditions. One is constant reflux ratio and second one is variable reflux ratio. So, both the conditions we have discussed and we have solved two different examples for both the one in each case for the solutions of the multi-stage batch distillation with reflux. In this lecture, we will consider very important design aspect of tray column by Panchon and Savarit method. So, let us start with this important topic for design of tray towers in a rigorous manner, Panchon and Savarit method. This method was developed by Panchon and Savarit independently in 1921-22. In this case, the variations in internal vapor and liquid flows inside a distillation column depend on enthalpies of the mixture. So, equimolar overflow, which we have assumed for the McCabe-Thiele method of design of distillation column, their rates are independent of the energy balance. So, we need not to have this change of flows inside the column, because we have considered only equimolar overflow for all the trays inside the column. So, we need not to have the energy balance for that, but to remove this assumption, we must consider the enthalpy balance explicitly. So, along with the component mass balance and the species mole balance, we need to consider the enthalpy balance equations explicitly with this. It is a more rigorous method and is free from the assumption of constant molar overflow. We need not to consider this constant molar overflow if we consider the enthalpy balance or energy balance equation. It is more rigorous than the McCabe-Thiele method. So, the use of this method is suggested if the enthalpy of a stream appreciably depend upon its composition. So, this method can be used when you have the stream which appreciably depends upon its composition. The enthalpy of the stream will depend upon its composition. So, in that case we can use the rigorous method. The Panchon-Savarit method is also a graphical method of solution of the material and energy balance equation, as well as the equilibrium relation taken together. So, this is similar to the McCabe-Thiele graphical method of solution. It is also the graphical Panchon and Savarit method is also the graphical method. In case of McCabe-Thiele method, we considered the material balance and the equilibrium relation together to construct the diagram and find out the graphically find out the number of ideal stages required for a particular separation. This method is also a graphical method, that is Panchon and Savarit method, and it requires the material and energy balance equation along with the equilibrium relation. So, all together can be taken and then the graphically we can calculate the number of stages required. Let us consider this multi-stage tray columns or fractionator as we have discussed before, and we have different sections over here. Section 1 which constitute taking the condenser, then reflux drum together, and then the envelope to consider the rectifying section. You can see over here, it is above the feed tray and it takes all part of the rectifying section. And section 3 it considered the stripping section, and this section 4 which constitute the overall fractionator. Now, let us consider the material and energy balance taken over envelope 2. So, that is the rectifying section. So, the total material balance in this section we can write, you can see G n plus 1 which is over here, then the tray entering gas into tray n is G n plus 1, and outgoing stream in this section is the distillate D over here, and the liquid which is coming out from tray n. So, which is Ln. So, Ln and distillate. If we do the total material balance in this section, it would be G n plus 1 would be equal to Ln plus D. So, this is equation 1. Now, if we do a component mole balance, component A balance, so it would be G n plus 1 into Y n plus 1, because its composition is Y n plus 1 which is coming to tray n, the vapor, and the liquid which is leaving having composition X n. So, it is Ln X n, and the D, the distillate which is taken as the overhead product in the rectifying section is D into X d. So, this is the component balance equation 2. Now, we have to consider the energy balance equation. So, if the enthalpy of the vapor which is coming to tray n from tray n plus 1, here tray numbering is done from top 1, 2, 3 as per the usual convention we use. So, the enthalpy of the vapor which is coming to tray n having enthalpy of Hg n plus 1, and the liquid which is coming down from the tray n having the enthalpy of HLn. Similarly, the distillate which is taken out having composition of Xd mole fractions of the distillate, and the enthalpy of the distillate is Hd. So, we can write the energy balance equation G n plus 1 into Hg n plus 1 would be equal to Ln H Ln plus D Hd plus Qc. So, because of condensation of the vapor at the top tray, if we just remove heat, say Qc for the condensation of the vapor, so that has to be added, which is taken out. So, Qc which is over here. Now, from equation 1 and 2, so this is now the overall mass balance and the material balance equation. We can write G n plus 1 into Y n plus 1 would be equal to Ln X n plus, if we substitute in place of D, if we substitute G n plus 1 minus Ln. So, from this we can write D would be equal to G n plus 1 minus Ln. So, this is substituted over here in place of D. If we rearrange or simplify, it would be Ln by G n plus 1 would be equal to X d minus Y n plus 1 divided by X d minus X n. So, this is equation 4. Now, here we assume that the reflux may be a subcooled liquid. So, if it is reflux is no, not saturated liquid, if it is a subcooled liquid that is below its bubble point in general, and x d is the mole fractions of the more volatile in it, then the energy balance equation 3, which is over here, in this case we can write, just simplify this, G n plus 1 into H G n plus 1 would be equal to ln H ln plus d into H d plus Q c by d. So, in this case it would be ln H ln plus d into Q d dash. So, this is Q d dash. So, here Q d dash is H d plus Q c by d. This is thermal energy removed from the top section of the column per mole of distillate. So, that is Q d dash. Now, putting d is equal to, from the overall mass balance, d is equal to G n plus 1 minus ln in equation 5, this is the equation. So, we can just substitute over here in place of d, that is G n plus 1 minus ln, it would be ln by G n plus 1 would be equal to Q d dash minus H G n plus 1 divided by Q d dash minus H ln. The quantity ln by G n plus 1 is the internal reflux ratio, because this is inside the column L by G ratio inside the column. So, it is called internal reflux ratio. Now, from equation 4 and 5, from these two equations we can write x d minus y n plus 1 divided by x d minus x n would be equal to Q d dash minus H G n plus 1 divided by Q d dash minus H ln, and then we can just rearrange it, Q d dash minus H ln divided by x d minus x n would be equal to Q d dash minus H G n plus 1 divided by x d minus y n plus 1. So, this is equation 7. So, we will just try to understand the significance of equation 7, which we have derived for the rectifying section. The liquid and the vapor concentration curves, that is HLX or XHL and YHG or HGY, that is the enthalpy concentration diagram, that similar to the one which we have discussed earlier, can be plotted. Enthalpy concentration diagram, the bottom one over here is blue line is HLX and the top one is HGY, enthalpy, vapor enthalpy and mole fraction, vapor mole fraction, and this is HLX, liquid enthalpy and mole fraction. So, the liquid and vapor enthalpy concentration diagram. A point on this diagram represents the composition and enthalpy of a phase, that is liquid, vapor or mixture. We denote this point by a term that also represents the flow rate of the particular phase. So, that is if it is a liquid, so it is L, liquid flow rate, and for that particular tray if it will be Ln or Ln minus 1 and so on. And similarly to the vapor phase, it is gas flow rate to different trays. So, each point on this diagram also represents the flow rate of a particular phase. Now, the point Ln represents the liquid phase leaving the nth plate. So, this is Ln shown over here, this represents the liquid phase which is leaving from tray N, and the leaving stream from tray N, if you think about the fractionator, it will go below to that tray which should be N plus 1, because the tray number is increasing from top to bottom. The entering plate would be N plus 1. The rate of flow is Ln mole per hour with enthalpy HLN and the concentration is Xn. The right side of equation 7, which is over here, the right side of this equation, that is Qd dash minus Hgn plus 1 divided by Xd minus Yn plus 1 is the slope of line through the points Yn plus 1, Hgn plus 1, which is over here at this location, that is Gn plus 1, and enthalpy having enthalpy Hgn plus 1, and the composition would be of the vapor phase on the enthalpy concentration diagram would be Yn plus 1, and it is passing through the point Xd and Qd dash. So, which is represented over here, which is V dash, point V dash. So, the left side is the slope of a line through the points Xn HLN and Xd Qd dash. So, if you look into this, this is also the slope of a line through the two different points, one is Xn HLN and another point is Xd Qd dash. So, that is on the enthalpy concentration diagram. So, the points, these 4 points, this point, 3 points and these points, these are X n H L n, Y n plus 1 H g n plus 1 and Q d and Q dash d are collinear, because from equation 7, which is developed for the rectifying section, considering the overall mass balance, species mole balance and the enthalpy balance equation, and these equations left hand side represents a slope passing to two different points for the liquid enthalpy concentration diagram, the liquid phase composition at that point and the fictitious point, that is V dash, which is Xd Qd dash, and also the right hand side is another slope of the line having two different points. It is a vapor enthalpy and composition point and the fictitious point Xd Qd dash. So, these 3 points should be collinear because their slopes are same, equal. So, the point Qd, Xd and Qd dash can be viewed as a phase obtained by subtracting Ln from Gn plus 1. So, this point, this V dash point over here is, it can be viewed subtracting Ln, that is this one, from Gn plus 1, that can be viewed. So, as we have done during the enthalpy concentration diagram and the conclusion we have made from the geometry of the enthalpy concentration diagram. We represent this point, that is Xd Qd dash by V dash over here, and flow rate of the phase V dash is also denoted by V dash, would be equal to Gn plus 1 minus Ln, because the V dash can be obtained by subtracting Ln from Gn plus 1. However, none of the phases can have the concentration xd and enthalpy qd dash, that is qd plus hd plus qc by d. So, this stream V dash is a fictitious stream. V dash over here is a fictitious stream defined solely for the purpose of graphical construction. The points D over here having coordinates xd and hd, and then V dash, that is xd and qd dash, are located on the enthalpy concentration diagram. Both are located on the enthalpy concentration diagram. V dash lying vertically above D because they have the same abscissa xd. So, for this point D having the same abscissa point, that is xd, and this V dash is also having xd. So, both of them lying vertically, V dash is lying vertically above the D points on the enthalpy concentration diagram. So, in figure the point D lies below the XHL curve. So, the reflux is a subcooled liquid here, because while doing the energy balance equations we have considered the reflux which is coming, or the condenser cooled the condensate from their bubble point. So, it is a subcooled liquid. So, it should lie from the saturated liquid composition line. So, which is that represents the subcooled liquid. Now, if we put n is equal to 0, because the entering feed or entering reflux from the reflux drum to the tray 1 we considered L naught. So, if we put n is equal to 0 in equation 7, in this equation, it appears that the vertical line joining the points D and V dash should intersect with HGY curve at y1 Hg, because these points are collinear. So, the point y1 and Hg is denoted by g1 according to the convention. So, if we put n is equal to 0, what will happen over here? This equation 7 we can write qd dash minus HL0 divided by xd minus x naught would be equal to qd dash minus hg1 divided by xd minus y1. So, this the vertical line joining the point D and V bar. So, this line should intersect the vapor at the point G1, which is shown over here, having the point y1 Hg. So, its composition would be y1 Hg1. The point L1 shown over here having the coordinates x1 HL1 is now located by drawing a tie line through G1. So, from G1 we can draw a tie line over here, and because x1 and y1 are in equilibrium for the ideal tray. So, if you have the equilibrium curve over here, so from this G1 point you can come vertically to the 45-degree diagonal on the bottom xy curve and go horizontally, which meets the equilibrium curve over here. Then if you go vertically to the HLX curve, you will find L1. So, you can join G1 L1 would be your tie line. So, next L1 V dash is joined to get the point G2. So, from L1 you can just draw a line from here, and this dotted line shown over here, which is crosses to HGY curve and it meets to the V dash. So, this point, the intersection point, you can find out for the G2. The graphical construction now proceed from one tray to the next tray according to this convention and find out the number of plates. So, the graphical construction now proceed from one tray to the next, and you can get similar points from tray to tray, G1 to G2 to G3 and so on up to Gn n plus 1, and also you can find from L1 to L2 to L3 and so on. So, you can find out different tie lines. Now, we considered equation 6 again, that is ln by Gn plus 1 would be equal to Qd minus Hg n plus 1 divided by Qd dash minus H ln. Now, inverting both sides and putting n is equal to 0, we obtain, if you put over here n is equal to L naught divided by G1 would be equal to Qd dash minus Hg1 divided by Qd dash minus HL naught. This equation if you invert, then you will obtain by inverting, you will get G1 by L naught would be equal to Qd dash minus HL naught divided by Qd dash minus Hg1. So, we note that HL naught would be Hd and G1 would be L naught plus D. If you do the material balance for envelope 1, if you just recall our tray column which we have considered at the beginning, and if you do the overall mass balance for the envelope 1, the vapor which is going up from tray 1 is condensed and distillate is taken out, the reflux L naught is returned back to the column. So, G1 would be equal to L naught plus D and HL naught would be the same enthalpy as the distillate taken out, Hd. So, now if we just substitute the values in this equation, you will obtain G1 by L naught would be equal to L naught plus D by L naught, which is equal to 1 plus D by L naught, which would be equal to Qd dash minus L naught would be Hd divided by Qd dash minus Hg1. So, if we define the external reflux ratio, which is L naught by D would be equal to Qd dash minus Hg1 divided by Hg1 minus Hd. So, this Qd dash and Hg1. So, Qd dash is over here, Qd dash, and Hg1, this is G1 having the enthalpy Hg1. So, this represents G1 and V dash, the vertical distance G1 V dash, that is this line, divided by Hg1 over here, this point, and the Hd which is having Xd Hd. So, this point. So, this is the vertical distance between G1 and D, that is Dg1, and the upper one is the vertical distance G1 V dash. So, this is the reflux ratio would be the vertical distance g1 v dash divided by vertical distance dg1. If the reflux ratio is given, equation 8 can be used directly to locate the point v dash. So, this is the equations we have derived, and reflux ratio is given, that is R is given. If R is given, this is equation 8, the first point D, that is xd, hd, this point is located from the known state concentration xd and enthalpy hd, because this is the outlet or the distillate taken out at the top product. So, its a composition and enthalpy is known. So, if this is known, a vertical line through xd intersects yhg curve at g1. So, this point condition is known and it will intersects over here vertical line, it will be g1. Then g1 is known. So, then the obtain v dash from equation 8. So, we can calculate v dash from this equation. So, if reflux ratio is known and other parameters are known, so we can obtain the vertical distance, that is v dash. Now, the stripping section. So, that is below the feed tray. The material and energy balance equation for the stripping section, that is envelope 3, this is envelope 3 in the stripping section, which can be written as total material balance, that is Lm bar would be equal to Gm plus 1 bar plus W, because you can see the entering liquid in this section, in the stripping section is Lm bar, and then outgoing at the bottom is W, and outgoing from Gm plus 1 tray is Gm plus 1 bar. So, Lm bar would be equal to Gm plus 1 bar, which is shown over here. So, this is total material balance, equation 9 is total material balance in the stripping section. Now, for the stripping section, if we do the component A balance, so Lm bar having composition of Xm is equal to Gm plus 1 bar having composition Ym plus 1 plus W having composition Xw. This would be Wxw. If we do the energy balance equation, it would be Lm bar into HLm plus Qw would be equal to Gm plus 1 bar Hgm plus 1 plus W into Hw. This is equation 11, that is energy balance equation. Now, if we just use the total material balance for this section, W would be equal to Lm bar minus Gm plus 1 bar. Then this equation 10 over here, that is the species mole balance equation, Lm bar Xm would be equal to Gm bar into Ym plus 1 plus Lm bar minus Gm plus 1 bar into Xw. So, basically W over here is substituted with Lm bar minus Gm plus 1 bar here. So, equation 12 can be rearranged to get equation 13, which is Lm bar divided by Gm plus 1 bar would be equal to Ym plus 1 minus Xw divided by Xm minus Xw. Now, we may write the energy balance equation 11, which is over here, the energy balance equation in the stripping section. We can write Lm bar HLm minus Gm plus 1 bar into Hgm plus 1 would be equal to W Hw minus Qw. So, by rearrangement we can write W into HW minus QW by W, and we can write HLM bar HLM minus GM plus 1 bar into HGM plus 1 would be equal to W into QW dash. So, QW dash over here is HW minus QW by W. So, this is equation 14. Now, if we use the total material balance equation in this rectifying section in this equation, so the stripping section equation 14 can be reduced to LM bar divided by V m plus 1 bar. No, this would be G. So, this would be, instead of V bar it would be G m plus 1 bar. So, we can write G LM bar by G m plus 1 bar would be equal to HV HG m plus 1 minus QW dash divided by HLM minus QW dash. So, this is equation 15. Now, from equation 13 and 15, so we can write Hg m plus 1 minus QW dash divided by Ym plus 1 minus Xw would be equal to HLM minus QW dash divided by Xm minus Xw. So, we will analyze similar to the rectifying section equation 7, we will discuss this equation in the stripping section and how to calculate the tie line and number of trays in the rectifying section. Extending the arguments put forward in the analysis of the rectifying section, we can say the points G m bar, that is having coordinates y m plus 1 h g m plus 1 and L m bar x m h L m and m dash x w q w dash, which is shown over here. This is m dash, this is m. So, they are collinear. The point m dash also similar to v dash, they are fictitious points, streams of concentration. The point m dash denotes a fictitious streams of concentration x w. So, which is shown over here, and enthalpy q w dash is equal to h w minus q w by w, that is the rate of enthalpy removal at the bottom per mole of the bottom product. And the flow rate will have w dash over here, which is L m bar minus G m plus 1 bar. Now, let us see how to proceed with the graphical construction of stages for the stripping section. The points M, which is having coordinates x w and h w, and m dash having coordinates x w q w dash, and they are on the enthalpy concentration plane. The output stream or the bottom product W leaving the partial reboiler is in equilibrium with the vapor generated in the reboiler and the entering the bottom tray. So, they will be in equilibrium, that is from the boil off, which is going from the reboiler to the bottom tray of the column, and the bottoms, that is the product which is taken out from the bottom tray. So, if there is a total NP trays in the column, we may call the reboiler as NP plus 1th tray. So, the flow rate as well as the state of the vapor from the reboiler is denoted by G Np plus 1 and G bar Np plus 1 and G Np plus 1 bar. So, this is the point and it should lie on the y Hg curve at the end of the tie line through M. So, which is shown over here. The line connecting GNP plus 1 and M dash intersects X HL curve and LNP by virtue of the collinearity condition given by equation 16. So, this is the collinearity conditions which we have discussed earlier, like in case of enriching section or rectifying section. Similar collinearity can be obtained from this correlation from equation 16. The tie line through Ln identifies G dash on Y Hg curve and thus the construction for the trace in the stripping section proceeds. So, from here like we did from the rectifying section, you can draw the tie line and then join the tie line with the M dash point over here and you will obtain another point on this line. So, again similar to that you obtain the tie line here and join to this point and get the next tray. As you move from the reboiler, you will move to the next tray, that is from bottom to the upper tray. So, it will proceed to the GNP plus 1 to GN NP and then GNP minus 1 and so on. So, similar to the procedure we followed for the rectifying section, we can do the similar approach for the stripping section as well. Now, let us consider the feed line. So, in this case you have feed conditions which is given and a changeover from one section to the other is necessary at the feed tray, and for this purpose we have to draw the feed line. So, consider the material and energy balance equation over the envelope 4. So, this is envelope 4, that is the red border envelope, the whole envelope which is shown over here in this column. So, if we do the total material balance, it would be F, which is feed is coming over here, would be D distillate which is taken out at the top, and bottoms which is W over here having composition XW. So, the component balance if we do for this, it would be F ZF would be equal to D XD and then plus W XW. So, this is the component balance, and energy balance we can write F HF, because enthalpy of the feed is HF, plus QW which is heat given to the reboiler, QW would be equal to DHD over here plus WHW, that is here, and the heat which is taken off, it is QC over here. So, the total material balance and component balance we can substitute for F from equation 17 in equation 18. So, if we substitute this F, that is D plus W over here. So, you will obtain D plus W ZF would be equal to DXD plus WXW. Now, XD denote the reflux or the distillate concentration, and these may be subcooled liquids. So, the notation is used XD, and we can write D by W from this equation 20 would be equal to ZF minus XW divided by ZD minus ZF. So, in place of x d now is substituted with z d. So, over here. So, similarly from equation 17 and 19 we can write f 17 is this one, the total material balance, and the 19 is the energy balance equation, and just if we substitute f over here. So, and then rearrange, we would obtain d by W would be equal to H f minus H d plus Q c by d divided by H w minus Q b by W. So, this would be equal to H f minus Q w dash divided by Q d dash minus H f. So, from equation 21 and 22 we can write, so we can equate these two and we can write H f minus Q w dash divided by Z f minus x w would be equal to Q d dash minus H f divided by x d minus Z f. So, this is equation 23. This is the equation considering the overall fractionator including feed, distillate and bottoms. Now, we have for all the sections we can draw the operating line for stripping section as well as rectifying section, and we can now draw or find out the significance of the feed line. Equation 23 shows that the points m dash, that is x w, q w dash and feed z f, h f and v dash x d q d dash. So, this is x w q w dash, this is feed point is z f, h f and this is x d and q d dash. So, these 3 points m dash, f and v dash are collinear from this equation following the argument of the rectifying section and then stripping section we have done before. So, the intermediate point which is f z f, f and having the coordinates z f, h f denotes the state of the feed in terms of the composition and enthalpy. So, it lies on the line joining m dash and v dash. So, this is m dash and this is v dash. As stated before, m dash represent a fictitious stream of flow rate w dash which is equal to L m bar minus G m plus 1 bar which is equal to W. So, V dash is another fictitious stream of flow rate D dash is equal to G n plus 1 bar minus L n bar which is equal to D, and F we can write from the total material balance, then F would be D plus W. So, which would be equal to D dash plus W dash. So, if a real stream can be viewed as a stream obtained by mixing the two fictitious streams, that is m dash and v dash. So, this f can be viewed as a mixture of m dash and v dash, two different streams, that is 250 such streams mixing together to obtain F, a real stream. The line M dash V dash is called, so with the line joining M dash V dash intersecting F is called the feed line. So, this distinguishes between the trace required between the stripping section and the rectifying section. So, thank you for hearing this lecture, and we will continue our discussion on the Panchon and Savarit method in the next class.